Practical announcement, there is still food. The very best food, of course, is gone, but but there still is food. At any rate, so this session is Gong Show, 5 speakers, and we start with Justin Berman.
Thanks, Finn. So let me start by thanking you all for coming and being here in Ann Arbor for these few days, and also to Finn, Vineeth, and Leo for putting this all together. I'm going to tell you a little bit about some work I'm doing with Hong, who's here now, studying the semi-classical limit of holographic modular flow. So just as a reminder of the semi-classical limit, ADS-CFT, we have a CFT where we're taking some parameter n to infinity, corresponding in ADS to taking the g Newton to 0 limit. And then there's this subalgebra subregion duality, which tells us that changes in the structure of the operator algebra in the CFT as we take the semi-classical limit leads to sharply defined geometric features of the bulk. So for example, the fact that single trace operators in the CFT are well defined in the semi-classical limit corresponds to the statement that there is a sharply defined causal wedge in the bulk in the semi-classical limit. Additionally, you find that the full boundary algebra has a nice geometric interpretation in the bulk as the full bulk entanglement wedge. But this in general means that this boundary of nice single trace, or this algebra of nice single trace operators is not the same as the full boundary algebra. And so what you find is that there is an additional operator, the modular operator, which defines some flow in the boundary algebra. And there's an expectation that the full boundary algebra will be obtained by using this modular flow on the single trace operators. You can get from just the algebra of single trace operators to the entire boundary algebra. So one thing that Hong and I have done is confirm these expectations and also show that the modular flow provides a boundary interpretation of extremal surfaces in the bulk by showing that these extremal surfaces exist exactly when the boundary modular flow has a fixed point in the algebra. So this is a nice abstract point about the modular flow, but to study more explicitly what's going on, we also looked at some examples. So one particularly nice example we looked at are these partially entangled thermal states, where you have a state that you prepare using a Euclidean path integral, somewhere along which you insert a heavy operator. Where by heavy here I mean it has a conformal weight that scales with the parameter n. And so in the semi-classical limit, it has weight that's going to infinity, and so it causes some back reaction on Euclidean geometry, such that it goes from a disk to some glued together pair of disks. And the Lorentzian geometry that this corresponds to is one with 2 black holes, each with their own effective temperature, but that share an interior. And what's particularly nice about this PETS is that you can explicitly compute the modular flow, the correlation functions of 2 modular flowed operators. And in particular, that you can show that these correlation functions are just analytic continuations of the standard correlation functions of single trace operators. So you can just study features of these analytic continued correlation functions and learn things about what exactly the modular flow is doing to your operators. I should also emphasize that although this particular example I'm talking about is a 2-dimensional example, it applies in d greater than 2 in some cases as well. And so now we're trying to use these explicit expressions to understand some features of the erratic end behavior that we expect to see in the semi-classical limit that Jonah talked about yesterday, and I think Hong will talk about a little bit more tomorrow, because it's exactly these kinds of operators in which we expect this erratic end behavior to become important. Thank you.
One question?
As in your second slide, do you have any comments to make about what happens to the boundary modular operator when we have exchange of dominant QESs in the bulk, such as in the case of an evaporating black hole?
We've thought a little bit about this, but I don't know that I have any particularly concrete comments to make about it.
Right. Thanks, Justin.
completely randomly.
We have another speaker from Michigan, Evan Detto.
Hi. So today I'm going to talk about some of my recent work with collaborators here at Michigan, Shabri, James, and Leo, who are all here at the conference. So in this paper, we looked at the fluctuations of giant gravitons in supergravity backgrounds. So we heard about the giant graviton expansion a lot yesterday. So this is one of the main motivations for our work. The idea here is that we have the finite n index for various holographic gauge theories, and it's known that this can be expanded in some form like this, where we have a term that's associated with Kaluza-Klein gravitons, and then we have some sum over different giant graviton configurations. So this particular version of the giant graviton expansion we're considering is not quite the same that Kostya had talked about, but a similar sort of idea. In this picture, these giant gravitons wrap cycles inside the internal space in the bulk. And in some sense, at least from the bulk side of this, one could think about the index as being built out of these giants. And since we understand the KK graviton and classical contributions, well, the real key to understanding the index from the bulk is these giant graviton fluctuations. So these giant graviton fluctuations have been studied from various theories from different perspectives. So, for example, like using indirect arguments from the superconformal algebra, and also in some cases from probe-brane actions in certain more supersymmetric sectors. So we look at the more general analysis of the fluctuations of probe-branes. So this is like a direct bulk computation of the giant graviton fluctuations. So we consider some cases of M and D branes in ADS cross S backgrounds, which are dual to well-known field theories. So as an example of computing these fluctuations for the scalars, since this is the most straightforward, we start with the dBi action. So this is like a integral over the C being the world volume coordinates, and then we expand the space-time coordinate fluctuations to quadratic order, and we can decompose these in spherical harmonics. So one kind of because the giants are wrap spheres. So one uses this to a quantum mechanics problem, basically, of these towers of modes. And so we can quantize and diagonalize this Hamiltonian. And then the fermions and world volume fields are a bit more complicated, but one can do that as well, and we did. So as an example, one gets a table of all the modes. So this is like the D3, for example, the scalars, vector, fermions. And then by summing over the modes with fugacities and various charges, we can get this expression, which Kasi also mentioned yesterday. And then that, for a single giant, that matches one of the first terms in the fluctuation part of the giant graviton expansion. And then we also looked at what happens if you consider stacks of giants. This is a little bit harder, but in some cases, one can consider promoting these modes to M by M matrices when we have a stack of M branes, and then we can get further coefficients in the giant graviton expansion. And at least in the half BPS case, you can get the full index to all orders. And just as some further directions, we're thinking about generalizing this to less supersymmetric space-time, so Sasaki-Einstein spaces, for example. And then also looking at the giant graviton expansion for other objects besides the index, so like non-protected quantities, by possibly including some interactions in the dBi action. That's all. Thank you.
Questions? Yeah.
Hi. You mentioned that you looked at the stack of brain example. Can you elaborate more on that? Like what kind of configuration do you consider?
Oh yeah, so this would be sort of like a non-abelian dBi picture where we if we have m different giants, there can be open strings between all the different giants. That's how these modes become like a m by m matrix. And then we're computing these further parts of these further terms in the giant gravitonic expansion, because if I go back here, there are different giant gravitonic contributions that correspond to stacks of branes, and each of these numbers tells how many stacks there are in different directions.
All right, let's thank Evan again.
Okay. Hello?
So the next speaker is Puxing Li. Puxing Lin, sorry.
Which one is the pointer? Hi, I'm Puxing Lin. I'm from UW-Madison. In my 5 minutes, I'd like to share with you some of the features of black holes in de Sitter space and to promote a very special black hole that deserves perhaps some attention, that also displays this phenomenon of continuous phase transition. So starting with some facts about de Sitter black holes, charged de Sitter black holes are described by the following metric. They have 3 horizons, an inner, black hole, and cosmological horizons. The phase space, or the parameter space, have this shape of a shark fin, where the boundaries are defined by the limits of the horizons. On the code line, RA is equal to RB. On the Nari line, RB is equal to RC. There's a special subclass of black holes solutions called the lukewarm black holes, for which the black hole temperature is equal to the temperature of the cosmological horizon. Now, when I mention temperature of the black hole, perhaps in your mind already there is some formulas popping out. It's no news that the temperatures of Killing horizons can be formulated in terms of the Killing vectors. In de Sitter space, especially when there's a black hole, what matters is the normalization, and this is where an observer comes in. We would like to describe the physics in some frame of an observer. And in order to do that, we can impose the condition that the Killing vector coincides with the world line of the said observer. In this case, the surface gravity corresponds to a horizontal acceleration measured with the clock of the observer. This introduces a factor into the Killing vector and a normalization condition. In asymptotically flat space and de Sitter, the observer is very conveniently located such that the normalization is almost trivial. It is less so for a situation with a black hole in de Sitter. And this introduces a redshift factor and also a condition where you identify the static observer by imposing a zero acceleration. One ends up with an expression for the temperature as such. As a sanity check, we can apply this to the Nari black holes, and one finds instead of having a zero temperature, these black holes have a finite temperature that corresponds exactly to the temperature of a two-dimensional de Sitter to static patch. With the temperature, one can proceed to compute laws of thermodynamics, which I will not talk about, but instead I'd like to point out a special point in the phase space of de Sitter black holes. The intersection of lukewarm and Nari line is a critical point at which the black hole undergoes a continuous phase transition. This is indicated by calculation of the heat capacity and its power law divergence upon choosing an ensemble of lukewarm black holes. And this is LW, sorry for the typo. We identify an critical exponent of 1/2. Now, these critical exponents distinguishes systems into different universality classes. Microscopic details are washed out at these critical points, meaning that if you have different systems very different systems belonging into the same universality class, the critical behavior will be the same. This also means that if you have a same system described by different degrees of freedom, different sets of degrees of freedom, the scaling behavior should be the same. So if you have an alternative description for de Sitter space and black holes therein, for example, maybe some matrix models, then you expect that the scaling behavior at the critical point is the same as that as one reads off from looking at gravity. So in our ongoing work, a goal is to complete the analysis by also identifying the remainder of the scaling, the critical exponents, which includes the correlation length, the divergence of it, and a vanishing of an order parameter. Notably, a diverging correlation length implies some massless or zero modes, and this happens to be consistent with the recent work that studies the one-loop partition function for near-Navier black holes. The authors, some also in this audience, discovered that the near-Navier modes changes sign when crossing this lukewarm point, or this critical point. So this is aligned with the idea that we have indeed a continuous phase transition happening here and aligns with the goal of our ongoing work. So I'll end here. Thank you for your attention.
I'm very impressed that all the Gong Show speakers are getting on time to 3 decimal places. So any questions? All right. Well, let's thank Book-Shin. The next speaker is Lisa Rosenberg.
Hello. So today I want to tell you about this fun project that we're doing with some collaborators at Harvard. It's based on this paper that we put out with Dan and Gabriel that showed that there's a correspondence at fixed central charge C between some partition functions of a matrix sensor model that we defined using a
You can turn it on. Oh, it's on.
Yeah, that's better. Thank you. Right, so the partition functions of some matrix sensor model that were defined using some constraint squared potential, where the constraint is some kind of crossing constraint for a CFT. And we showed that this is in correspondence to partition functions of 3D manifolds up to factors of h bar. I'll explain in this action what h bar means. It's some parameter that tells you how much your potential deviates from satisfying the constraint. So the constraint consists of these 3 pieces. So you have the 4-point invariance of a sphere partition function, the S modular invariance, and the 1-point modular invariance on a torus. And so each of these is squared inside these terms. And so that's how you get this constraint squared potential. And h bar going to 0 enforces the constraint to be satisfied. So building this model and integrating over some CIGKs, which are the OP coefficients of irrational CFTs, which we believe are the possible CFT objects that might be dual to gravity in some ensemble. And this integral over weights of the matrix part of the model. We can interpret this also as being a potential that expands us around Cardi. So the single trace potential is defined to give Cardi density of states for a fixed spin as the leading order contribution. So we define this partition function, and basically we focus on the diagrammatics of what's happening with the terms that we introduced. And it's very geometric, so we focus on V4 for the purposes of this talk, because those are easier to handle. There's no like mapping class group questions that usually arise when you analyze partition functions for 3 manifolds. So we focus on V4, which is purely tensorial. It's only dependent on CIJKs. And we construct diagrams that result from this model. The main thing is when you have Wilson lines, closed Wilson lines, that you build from these pieces, which are the vertices and the propagator of the tensor model. The main rule is that when you have a closed Wilson loop, you do hyperbolic surgery on it. So you take some tubular neighborhood around it, you cut it out, and then you insert it back in with something that's dictated by the matrix model. And in the leading order, it is a disk. So for example, this allows us to delete these genus holes that are formed in the geometry. So it literally inserts the CARD, which is reversing which cycle is contractible. So then you delete the hole. But we know that these objects, these vertices and this propagator correspond to very specific functions that are obtained from analysis like Virasoro to QFT. So this Virasoro 6J symbol is very important because it has tetrahedral symmetry. And this guy is actually what allows us to build up any possible link. So there's a theorem in math by Licorice that allows you to build to derive the partition function of any three manifold from doing surgery on a closed link inside S3, a three-sphere. And this allows us to show that all closed manifolds are generated just by using these diagrams, up to factors of h bar. So that's actually a very important point. What is this factor of h bar? Also, we don't expect there to be any h bar in an actual gravity theory. So the main thing that we notice is that you can generate the same manifold with different factors of h bar. For example, we saw before that there's this vertex, this pillow vertex, that comes with a factor of 1 over h bar. But we can also form the same manifold by combining two 6Js, and then it comes with no factors of h bar. And more generally, we can package this into this expression where z 3D gravity is the partition function for some fixed manifold defined by the link, for some fixed c, the central charge. And then there's this purely combinatorial factor f, which only depends on h bar, and it's some polynomial of h bar. And we want to understand what this function is, because it would tell us with what weight we need to sum over possible manifolds. That's okay. So yeah, that's what we're trying to work out, and you have to check all possible left-hand side manifolds, and like you can stare at these guys meanwhile. But yeah, this is a very fun geometric problem, but also tells us something deep about the sum over three manifolds in gravity. Thank you.
Any questions? One question.
Thank you, Lisa. I guess where are we at for constraining F? Like, is nothing known at all, or is there are like some kind of symmetry considerations that constrain the form of F?
So F is as I mentioned, it's a purely combinatorial thing, so it doesn't actually depend on the theory. So in principle, this is something geometric that we can derive by considering like what kinds of diagrams can be produced, et cetera. But we only like conjecture that it goes to 1 at h bar going to 0 because we don't expect, like intuitively maybe we should just sum over all manifolds with weight 1. But yeah, I guess that's what we're checking. Yeah.
Okay, well, let's thank Lisa again. And the last speaker of the Gong Show is Xiaoyi Shi. Sure, the answer is no.
Oh, yeah. Yeah, okay, hello everyone. Today I'm going to talk about the question whether black holes can preserve more than 4 supersymmetry. And the answer from our experience is no. So all the known microscopic BPS black holes in string theory preserve at most 4 supercharges. A standard example is the 4D n=4 supergravity, where the regular large BPS black holes are typically 1/4 BPS days. And if one tries to increase the number of supersymmetry they preserve by setting, for example, the electric charge to be 0, the duality invariant quadrant will vanish and the black hole horizon area shrinks to 0 at the 2 derivative level. So this motivates us to ask the question, is there a general principle that forbids BPS black holes from preserving more than 4 supercharges? And we decide to answer this question from the low energy effective theory. So universally, extremal black holes develop a long ADS2 throat with emergent 1D conformal symmetry, and moving slightly away from extremality softly breaks this conformal symmetry. The resulting leading order dynamics is governed by the Schwarzian modes plus possible R symmetry and gauge boundary modes. And since BPS black holes are extremal, we can address the n greater than 4 question by looking at the universal near horizon effective field theory. So our strategy is first to classify all the allowed 1D superconformal groups, and then construct and quantize all the associated super-Schwarzian theories. And then we need to impose physical conditions to find realizable theories to describe near BPS black holes. So on the left is the complete list of the supergroup that contains SL2R as a bosonic subgroup, and each of them defines a local superconformal algebra and gives a candidate super-Schwarzian theory. And its bosonic action is given by the Schwarzian derivative for the reparametrization mode and the connected term for the R symmetry mode. And these are fixed by the group theory information like the fermion representation. And we further quantize all these super-Schwarzian theories using the method of fermionic localization. Namely, we compute the partition function by localizing the path integral on the fixed point of a U1 symmetry generated by the super-Schwarzian action on the symplectic integration space. And we find the one-loop exact result. And after constructing all the theories, we need to impose physical requirements. The first is the unitarity. So here I show the example from the OSP 4-star 2N family of Schwarzian theories. And we notice that the SU2 mode has a wrong sign connected term. And in the full path integral, we need to sum over all the integer shapes of the SU2 chemical potential, since they preserve the same boundary condition. So the wrong sign connected term will imply the divergence in the partition function. So for this reason, the OSP 4-star 2N and SU1,1N family are excluded because they cannot describe the unitary quantum black hole. And on the right, I show the anticommutator with or without the inclusion of a nonlinear term in the SU2 charge. So because the super-Schwarzian theory should describe the near horizon sector of a higher dimensional black hole. So all the charges are inherited from higher dimensions. And usually the algebra should be a Lie superalgebra, so meaning they are linear. So we have to exclude all the theories that has a nonlinear algebra in the anticommutator. And it turns out that all the super-Schwarzian theories with n greater than 4 violates either unitarity or the linear conserved charge algebra constraint. And they leaves only 4 near horizon theories. So we have 2 familiar ones, the n equals 2 and n equals 4, which describe the near BPS black holes in ADS and flat space. And we discovered 2 new theories, the n equals 3 and large n equals 4, which describe the near BPS black holes in asymptotic ADS3 cos S3 cross S3 cross S1 background and its D2 quotient. So as a summary, we construct and quantize all the super-Schwarzian theories, and with some assumption, these theories cannot have more than 4 supercharges. So the BPS states cannot preserve more than 4 supercharges. And we apply the spectral results to analyze the BPS spectrum in this background in the companion work. Thank you.
So, any questions?
In the case of the nonlinear theories, do we have any argument that would rule them out in ADS3 that does allow these nonlinear brackets? Or do you think that those are still okay, basically?
Yeah, actually, we don't have the argument for the If we just restrict to the near horizon region, ADS2 or ADS3, actually the n greater than 4 theories that realize a nonlinear anticommutator can exist, and there has been some constructions in the literature, but we believe they cannot be the near horizon theory for the higher dimensional black holes.
Okay. Yeah.
Oh, yeah.
Okay, well,